We're coming now finally to the Open Computer Vision interface. If you start it up, you get this image here with the workboard here and here with three different riders. The first one, we can manage the datasets we're loading. Currently there's a nameless one and we load the data. For example, the XRF data. Then we can give the whole dataset's name XRF and tell him that we now define it to be the integration of the channels of 1 to 2000. Doesn't look too good, but doesn't matter for now. Then we can say create a new dataset and load the hyperspectral data, the reflectance imaging spectroscopy data. And we get here a nice image that's rather close to what we normally see. And we can now move it a little bit to the side. Here we have the image transform jumper. We have here the offset, which is how far we can move it. We can also stretch it or not stretch it. We can have a certain gradient in the intensity. And we can also change the general scale, but this is only in relation to others. We can do large rotations. And we can do also small rotations. There's also the possibility to warp an image with a pre-calculated warp matrix, but we come to this later. What we now want to do is we want to align the reflectance imaging spectroscopy image with the XRF image. However, for this we need to detect features in both images that are similar. Now we can look at this image, and the two main contributions to making this image darker are either the iron-based red and pink ink and the copper-based Egyptian blue in the color. In addition, we also have there the black carbon paint, which was used for the hieroglyphs, but we unfortunately cannot detect that with XRF. So we go back to the XRF data, and we can open the Inspect Data dialog and look at the data set. Now, you have to believe me, I know this data set. We have here the average spectrum, and we have here from 413 to 439 the iron image. Not the iron image, but the iron signal that we get here. And then we can also have here from 525 to 548 the copper signal. And we're now having an image that's rather comparable to the optical impression. It's now important what I did here is basically negative means it's a negative contribution. Everything between these brackets is normalized. The semicolon is separating different part. Everything is explained down here. Good. Now, if we want to use this as a reference, we want to use it as a master image. So we say replace master. And if we now switch to the reflectance imaging spectroscopy data, we see it stays there aligned. Other functions we have here is we select the data set, create a new one, delete the current one. We can change the order of the data sets, which is only important if you're stitching 5 or 6 data sets, then the order of the list is determining in which order they are added up on top of each other. You can set the name of the data set that's calculated from. You can use an external file as an image, we will come to this later, and you can calculate an RGB image. You can save the base image, which is the one that you're currently seeing. You can save the flat image, which is an image after modification. The Inspect Data dialog we've already seen. Add to master means it's done additionally a part of it, replaces it, or you can also save the master image, which is nice if you're just trying to stitch together some photographs. Now, what we could do is we could now start trying to move things around until they more or less match. Problem is that's very labor intensive and will normally not be satisfying. The alternative is to really use the Open Computer Vision library and detect features. For this we go up here to the options, where we have to select between two different routines for this, SIFT and ORB. both detect features and images, and in general, SIFT is better than ORB. Problem, however, is SIFT is not really freely available. You may use it for scientific means, but you cannot easily or without buying or paying use it for commercial means. So SIFT is only for science. If you select these two methods, you have here also options that you can vary. They're basically just from the OpenCV library and entered into this graphical user interface. Good. Further, what you can also say is if you want to crop the image, you can, for example, tell him here, okay, if you select crop, he is, if you enter there the coordinates, capable of then cropping out a part of the image and leaving out the edge. If you want it, it's useful, otherwise leave it. The most useful thing to change is the lowest value. It's a maximum number of features that are detected. If we're now having these two images next to each other, we've selected SIFT, we just say detect features, and we're having here a list. And the first one looks already okay. Next one is okay. This one is okay, okay, okay-ish, okay, okay. This one is a misfit. It's not really in good agreement, so we can just delete it. Good agreement, misfit. With Control D or with this button here, you can delete them. Delete. And you see here are now the hieroglyphs detected, which are not even in the XRF scan and do not have any XRF signals. So, away with it, good. We are now having here a number of features. We can see them here in this screen, or we can have a closer look by selecting his split. Then we're always having here the magnified area. By pressing Shift and left clicking, we can zoom in. By right clicking, we zoom out. Good. As we now have a number of features, we can just say calculate a transformation. We can also say estimate a translation, then he's only doing a rotation and a translation. But with a transform we really do a warping, and we can put these different images on top of each other. This looks okay-ish. We can now have the active image height, make it transparent. And if we make it transparent, we already see here very ugly shapes. This is not really a good alignment of the data sets. And there are some reasons for that, because we made it admittedly a little bit difficult. Now first, we switch off the Apply Image app, warp, and then move it back. Now, first point is, the images have a different resolution. So the XRF beam was rather coarse, so things are in this image that do not really belong there. So we can modify this image. For this we go here, say Save Flat Image, and then we just say HSI Flat. We replace it, then we can go there and have the image here. The first point is, what is really annoying are the hieroglyphs, because they do not belong here. Or well, the hieroglyphs belong there to the image, but we want to have them out because they make the detection of features rather complicated. I have now already wiped them out with GIMP, but I couldn't show you because there's an interesting bug between my screen recorder and GIMP. Then we can go also use a filter, use a Gaussian blur effect, and say that we will use now here a value of 1.5, which is a good combination, to give it an apparent resolution comparable to the XRF data. Now we can export it as, where are you? Flat Gauss blur, and export it. Then we go back here load a flat image and say we want to have the Gauss blur instead. And he's showing it nicely. Another thing, to make it easier for him, this is a little bit in a different aspect ratio, we can already stretch it a bit, so that it's now more or less the same distance. Now we go back and say detect features. And indeed, this is starting rather promising. Strong is bad, so remove it out. Okay. Good. Yeah, this is not going too well, so okay. No, this looks similar, but it's not on the height of the nose, so it goes out too. Okay. Oh, okay. And you should also never be afraid to just simply help him a bit, because this is an interesting feature, and we can go there now. Say it's here. So we say replace. Good. This is also not identical, so we also say here replace. Delete it. Okay. Yeah. Nice. Wrong. Yeah. Clearly not part of this. Nope. Looks reasonable, but we cannot use it. Okay. No, this is also wrong. Good. We are now having 16 features. What you need to take care of when you do some image warping is that the features are more or less evenly distributed about the area that you want to warp to. Because otherwise you get some strange deformations, and it's especially a problem if you have good features only in the center of an image. But yeah, let's see. I know that there is for data sets that have much more similar features, there are better methods for stitching them, but this is what worked for me in one paper that you see in the reference. So if you're happy with it, you may use it. Otherwise, go find your own solution. So we're having here now a whole number of different features. Here we can still easily add one. Here in the middle, in the broken line. And after we have all of them, we just say calculate transform. As we have still the apply image warp set off, we can now switch it on. No. So let's go back. We want to have the normal screen, and we want to have the aligned image. And here we now see that they are much better aligned than before. So the lines really run here very nicely on top of each other. And this is now something where we can say merge to master, which means that the current image is merged on top of the master, and as are all other data sets that are currently but the one creating the master. We can also say merge all images, which in this case would result in quite a failure in the program, because the data sets have different numbers of channels. We can also save the list of data sets we have here and load a list. So we now say merge to master, and we call it his aligned 2. Good. Now we create a new set and load his aligned 2. And we see it looks rather reasonable. We can now go back to the RIS data and have them superimposed, and yeah. There are now of course a little bit of differences due to interpolations, but yeah, in total satisfying and now suitable for data fusion in the batch generator. So, I hope this helps.